Hello and welcome back to another video on the foundation degree in integrated engineering and another mathematics and control. This is the second one, and we're following on from what we did last time with the first order differential equation, and we're doing second order differential equations. The second order differential equation is the first system we'll get in this control where we get feedback coming into the system. So we're now looking at feedback systems. So we'll discuss a little bit as we go through the examples where damping and that is present. Right, so there are two real types of second order differential equation, which is the homogeneous equation and the inhomogeneous equation. They're very similar in calculation. Okay, if your equation is equal to 0, for instance this, then this is homogeneous. Okay, this makes the solution very slightly simpler because there's one less step in the calculation. If your equation is equal to some function of x, for instance that, then that is an inhomogeneous function, and this adds one step into the calculation. But what we tend to do when we talk about solving second order differential equations is have all the steps in the general rule to solve it, and as a mathematician or as an engineer we understand which steps we need and which we don't. Okay, so moving on. So there's two things we have to work out with a second order differential equation to get the solution for y in this case. One is the complementary function, which is defined by y CF, and one is the particular integral, which is defined by y pi. Okay, and I always find it's best to explain the process with the examples, and you guys want worked examples, so we're going to do a worked example on both a homogeneous first and then an inhomogeneous second order differential equation. I'm going to start with one like this. So we've got an equation. Okay, now if you are asked to find the general solution for a second order differential equation, you may not be given this part in a question. If you're asked to solve it, you will always be given these, which are the boundary conditions. So what we're saying is, for this equation, when x equals 0, y equals 0, and dy over dx equals 2. Okay, so in a homogeneous second order differential equation, the particular integral is in any second order differential equation, the particular integral is determined by the form of the right hand side of the equation. In a homogeneous one, this is 0, so the integral of this is also going to be 0. So the particular integral for an homogeneous equation is always 0. So we can skip that step. Okay. So the second part is to work out the complementary function. Now initially with the complementary function, what we need to do is find what type of differential equation we have. There'll be more on that coming in a minute. Okay, and this is done by creating the auxiliary equation. Now what effectively we do is we replace our dy dx by k. So d squared y dx squared becomes k squared, dy dx becomes k, and y becomes 1, because it's effectively k to the power of 0. Okay. And now we've got a quadratic equation that is equal to 0. So we can solve it, and the roots of the quadratic equation will determine what type of complementary function we need to use. So looking at this does factorise. You might not be able to see it. It factorises into 2k plus 2 times k plus 3, and so our roots are k is minus 1 or k is minus 3. Okay. Now these roots are important in control systems in that we need our roots to be negative. Right, so you'll see in the textbook that the real part of roots of a control system must be negative for the system to be stable. Okay, so we're okay, we're a stable system here. Okay, now the type of roots we get determine what type of complementary function we use, and there are three. Okay, so type 1 is where the roots are real and different. That's the type we currently have, and this is the equation we put in for the complementary function. So you just look these equations up and write them in. Okay, they've been determined by people far cleverer than us. Type 2 is where the roots are real and the same, and type 3 is where our roots are complex numbers. Okay, and we're going to talk about complex roots in a bit. Okay, now in terms of control systems, type 3 is an underdamped system. You can actually work that out because we've got both an exponential part and we've got a sinusoidal part. So that will trace out what we always commonly see as an underdamped response, where it rises and then oscillates around the set point, decaying until we get to the set point. Okay. If the roots are real and the same, then the system is critically damped. Okay, and if the roots are real and different, then it is over damped. So it's actually got too much damping for what we need. Okay, and an overdamped system is actually technically two first order systems multiplied together, if you look at the way we can build the quadratic. Okay, so our system was real and different because k1 was minus 1 and k2 was minus 3, so this is our complementary function. We put the values of k. It doesn't matter which we set k1 and k2. Whichever we set k1 and k2, a and b's values will be calculated to be different to make things balance up. So typically you just put the first one in k1 and the second one in k2. And we're left with a complementary function as being a e to the minus x plus b e to the minus 3x. We put that together with a particular integral, which in our case was 0 because it's homogeneous. And so our general solution for this is that y is equal to something, a, e to the minus x, plus something else, b, e to the minus 3x. Plus 0, but obviously we're going to ignore that. Okay, so now our boundary conditions come in. Okay, so that's our complementary function. That's our particular integral. Okay, and our boundary conditions will allow us to work out what a and b are. Okay, so our boundary conditions were that x is 0, y is 0, and dy dx is 2. So when x is 0, y is 0. So we put that into our equation. Okay, so 0 is a e to the 0 plus b e to the 0 plus 0 from the particular integral. So we get that 0 is a plus b. Now, other than now working out that a is minus b or b is minus a, we can't do an awful lot with that. Okay, so what we have to do is now find another equation that's got a and b in it, okay, so that we can determine them both. So we need to get two equations because we've got two unknowns, and that's why we differentiate. So if we look at our boundary condition, we've got a boundary condition for the differential of y as well. So we need to differentiate this function to determine what dy dx is. So it's a relatively straightforward one to differentiate. Multiply by the power and leave everything else the same. So we get that dy over dx is minus 1a e to the minus x minus 3b e to the minus 3x. We know our boundary conditions for this, that dy dx is 2 when x is 0, so we plug those in. We get that 2 is minus a e to the 0 minus 3b e to the 0. E to the 0 is 1, and so we get this equation as a second equation in terms of a and b. So now we need to use simultaneous equations to solve these two equations. They're quite straightforward because we actually have one lot of a in both equations already, just one happens to be negative. To get rid of that, we add these two equations together. 0 add 2 is 2, a add minus a is 0, and b add minus 3 is minus 2. So we get 2 is minus 2b, and therefore b is minus 1. From that, we can then establish that if 0 is a plus b, then a must equal 1. And so our particular solution for this system is that y is equal to 1e to the minus x minus e to the minus 3x. And if you want to check that, you can put x in and check that y comes out as 0. If you want to double check it, put your values we've just calculated for a and b into the differential equation we worked out, and it should come out as 2. Okay, so that's the homogeneous. The inhomogeneous, slightly trickier, and I'm going to give us a slightly trickier one to do as well, just to make life easy for myself. So we've kept the same boundary conditions, you can see that. Okay, that's just so in the making of this video I don't forget which boundary conditions I'm using. Okay, if you're asked for a particular solution, you'll always have these boundary conditions given, but they can be anything. Okay, see here now we have a function of x on the right hand side of our equation, and our left hand side is now 4d squared y dx squared plus 4dy dx plus 145y. Okay, so our equation is slightly trickier. Now, I've just noticed an error here. This should say inhomogeneous, not homogeneous. Okay, and the particular integral, we start with what all the textbooks and everyone online will call a trial solution, and what my lecturer called a first guess. Because in essence what we're doing is guessing what the answer is. But we're guessing what the answer is logically based on what the right hand side of our equation is in the question. So here we are 2x plus 3. That is a linear equation for x. Okay, so our trial guess needs to also be a linear equation. If this were a constant, our trial guess would be a constant, and that's kind of seen in this table here. Okay, so our particular integral is going to be in the same form as that right hand side of the equation, but we don't know what the numbers are. So as we were 2x plus 3, it's a linear equation in x. Our first guess, or our trial solution, is going to be cx plus d. So that's what we do. Okay, if we were an exponential, we'd be an exponential. Okay, if we were a quadratic, we'd be a quadratic, and so on. So here's our function, here's our boundary conditions, and we've said, right, y is cx plus d. Okay, that's our trial solution. What we're now going to do is try and work this into this left hand side of the equation. So you'll see we've got y, this will be our ypi for what we're doing here. dy dx, so we'll need to differentiate it to get dy dx, and d squared y dx squared, we'll have to differentiate dy dx, or we'll have to do the second differential of y. So that's what we do next. We differentiate this function twice. Now the differential of cx plus d, d is a constant, will disappear. C times x differentiates, so dy dx is just c and the differential of a constant is 0, so d squared y dx squared is 0. So now we have y, we have dy dx, we have d squared y dx squared. We take these values that our guess has told us the answer is going to be and put them straight into the equation. So what we have is 4d squared y dx squared, which is the 0, plus 4 dy dx, which is the c, plus 145 times y, which is cx plus d. And that is equal to what it was equal to originally. So we're keeping everything equal, we're just substituting in what our guess says that these values are going to be. Now, working this out, obviously that will disappear. We're left with 4c plus 145 cx plus d gives us that. Okay. Now what we're going to do is equate coefficients. So we're going to look at the left hand side and we're going to look at the right hand side. Because they are equal to each other, then anything times x on the left hand side is equal to anything times x on the right hand side. So all we've got on the right hand side times x is 2x. All we've got equal to multiplied by x on the left hand side is 145 lots of c. So that gives us 145c times x is equal to 2x. And similarly, everything else on the left, 4c plus 145d, must be equal to what's left on the right, which is 3. So we get 4c plus 145d is 3. Using that first equation, we can work c out very quickly. 2 divided by 145, so our c is 0.0138. We then plug that into our second equation to get that 4 times c plus 145d is 3, and rearranging that for d, we get that d is 0.02. And so our particular integral has been completed. We've got all the values, and our particular integral is 0.0138x plus 0.02. Keep that to hand, we're going to need it in a bit. Okay, but for now we'll leave that bit alone. Okay, then we step on and we do the complementary function. The complementary function is done exactly the same way as for an homogeneous. Okay, we've already dealt with the right hand side of this equation, so we make the equation equal to 0. Okay, so we've got 4 d squared y dx squared plus 4 dy dx plus 145y is equal to 0. We produce the auxiliary function, and then we find the roots of that function. Okay, now you are not going to be able to factorize this function, I promise you. Okay, so we use the quadratic equation. With the quadratic equation, I've plugged in my numbers there, and we end up with a tiny little snag that it's asking us to do the square root of a minus number. Now, depending on the complexity and age of your calculator, it might let you do the square root of a minus number. It might tell you that that's a mathematical error. Okay? Now, we need to bring in what we've done on complex numbers and understand that we can determine what this root is, but it's a complex root. Okay? So, if we have minus 2304, the square root of that, okay, but we acknowledge that in complex numbers, j for an engineer, I for a mathematician, but we're engineers, so let's get j, is the square root of minus 1, then this function here, this square root, becomes the square root of minus 1 times the square root of 2304. So we can write it as minus 4 plus or minus j square root of 2304, all divided by 8. Root 2304 is 48, so we get that k is minus 0.5 plus or minus j6. Your complex roots will always be in this form. There will always be the complex conjugate of each other. Okay, it's how complex roots work, and you'll always have two complex roots in a second order system. You won't have one real and one complex. You'll always have a pair of complex roots. Okay. So our roots are complex. That was, if we remember back to the table, type 3. And so our complementary function looks like this. Now this, although the process is exactly the same, this is obviously going to be a little bit harder to work with because it's a little bit more complicated. Okay, but this is our general rule, and alpha is the real part of our complex root and beta is the j part of our complex root. So in this case, our complementary function is going to be e to the minus 0.5x on a cos 6x plus b sine 6x. Now's the point where you need to remember that this is inhomogeneous. Because if you forget to add in the particular integral now that we worked out earlier on, before trying to work out what a and b are, you will get the wrong answer. So we need to acknowledge that our value of y, the general solution for our value of y, is given by this function here. Okay, so we've got the complementary function here and the particular integral here. Okay, we need both because we're working out what y is, not y complementary function with the boundary conditions. But we have some boundary conditions. Brought them in. I've brought them back here. Okay, so y is 0 and x is 0. So now let's plug them in. So we get that 0 is equal to e to the 0 on a cos 0 plus b sine 0 plus 0.0138 times 0 plus 0.02. Now if we're looking at that, that's 0 obviously, sine 0 is 0, cos 0 is 1, and e to the 0 is 1. So that all cancels down to say that 0 is equal to 1 times a plus 0.02. What that means is a is minus 0.02. So we've determined a already, but we need to differentiate to determine what b is. So we need to differentiate this function. Now I'm hoping you guys can work out that the differential of 0.02 is 0, the differential of 0.0138x is 0.0138, so these two we're going to ignore for a second and put them in at the end. They're easy enough to do. As long as we remember to put them in at the end, it's fine. I want to focus on this part of it, because what we've got here is a function times another function. So what we need to use is the product rule. Okay. And the product rule on this part says that the differential of y with respect to x is v times du dx plus u times dv dx, where u is one of the functions and v is the other function. Now I'm going to select e to the minus 0.5x to be my u and a cos 6x plus b sine 6x to be my v, for no other reason than u comes before v in the alphabet. Okay. It is a bit stricter with the other rules, but with the product rule we can pick whichever one we want. Okay. So what we're going to do is differentiate this part of the function using the product rule. And we start with this. Now I'm very structured with my product rule. Okay. I write my rule and then I write what my u is and differentiate it. So I pick e to the minus 0.5x to be my u, and I differentiated it straight away. So I've now got what my du dx is. I then pick the other function to be my v, and I differentiate it, and I write it in a grid like this, because then when I come to my rule I can say, right, v is a cos 6x plus b sin 6x times du dx, which is minus 0.5 e to the minus 0.5x, and I can look at those two functions and say, you know what, I'm not going to write it that way round because that doesn't look nice. So what I'm going to write is minus 0.5 e to the minus 0.5x times a cos 6x plus b sin 6x. And similarly, I'm going excuse me, I'm going to factorise out a 6 and multiply it by my u to get my differential function for this bit to be minus 0.5 e to the minus 0.5x, which is my du dx, times a cos 6x plus b sin 6x, which is my v. So that's my v du dx, plus I've taken a minus 6 out, so the plus becomes minus, times it by e to the minus 0.5x, which is there, so that's my u, with a little bit of my dv dx. Because I've taken minus 6 out here, this has to become minus here to keep the plus function. Okay, so I've got v du dx plus u dv dx. What I then need to do is add in the final basic differential of 0.0138, which I've got here. Now I know what a is because we worked that out earlier on, so I can put my value of a in, and now all I need to do is work out what b is based on what's happening here. Okay, so dy dx is 2, x is 0, so we plug those in. So 2 is minus 0.5 e to the 0 times minus 0.02 cos 0, cos 0 is 1, plus b sin 0, sin 0 is 0, e to the 0 is 1, sin 0 is 0, cos 0 is 1, and that is still 0.0138. So if we go through all of that, cancelling where we can, we get minus 0.5 times minus 0.02 minus 6 times minus b plus 0.0138. So we get that 1.976 is 6b. That's just taking all of the numbers across to the left hand side and subtracting them and multiplying minus 6 and minus b to get plus 6b, and from that b is 1.976 divided by 6, which is 0.329. So now we've got a and b for our function, we can get the solution to the problem. Let's remember to put the proper particular integral back in, not the differential of it. Okay, and we've got what y is. Okay, now from this, if we want to check it, we can put 0 in for x all the way through this and check that y comes out as 0. We can also put these values for a and b into the differential function we determined for this on the previous slide and work out that the answer gets to 2. There are 2 checks we can do to make sure we've done it correctly. Okay, that is how we solve second order differential equations. What we're going to do next is look at how we can use Laplace transforms to make that process slightly easier. So I'll hopefully see you then. Goodbye.